Okay, so this will be the first lecture out of chapter 7. So we're going to jump from chapter 3 to chapter 7 because I think it's easier to understand chapters 4, 5, and 6 if you understand chapters 7 through 11. Because I like for students to understand things at the fundamental level, at the atomic level, the structural level. So if you understand structures of molecules, then understanding chapters, which is what's covered in chapters 7 through 11, then you can understand chapters 4, 5, and 6 in more depth. Okay, so in this chapter, basically we look at the structure of the atom in more detail. Because right now we have our chapter 2 model of the atom, right? We just have a nucleus and an electron cloud. Well, it turns out it's a little bit more complex than that, and so that's what this chapter covers, is the complexity of an atom. And so in order to understand the content in this chapter, we had to cover some basic physics first, particularly the physics of waves. So if we have a wave, so what are some of the basic properties of waves that you may know? If you've had a science class, physics class in high school, then surely you've covered some basic properties of waves before. So some fundamental properties of waves would be a wavelength. Right? So what is wavelength? So if you take any 2 points on a wave, it would be any 2 similar points on a wave, it would be the distance between them. So typically it would be from crest to crest, right, or trough to trough, but it doesn't have to be. It can be any 2 similar points on a wave. The distance between them is wavelength. Right, so what's a distance? And so it would have units such as meters, for example. And so it's given the symbol, right, the Greek symbol lambda. Okay, so what are other features of a wave? So another feature of a wave would be frequency. So what is frequency? So let's see. So if you were standing here and you count the number of waves that go by in a second, so if you count the number of waves that go by, and so we'll say the wave is moving this direction, for example, from left to right. So if you count the number of waves that go by per unit time, and that per unit time is typically a second, then that would be the frequency of the wave. So it has units, so it's given symbol. It's the best I can draw it, so that's the Greek symbol nu. And so it has units of number of waves per second, or 1/2, or seconds to the -1 power, right? And so the inverse second, basically. So an inverse second is the same thing as 1 hertz, right? Given the symbol Hz. Okay, so other features of a wave. Would be its amplitude. And its speed. So we'll say a little bit more about that. So amplitude would be basically it's the maximum displacement of points on a wave. So it would be measured, for example, from half height, so that would be its amplitude. And so we're not going to worry about amplitude in this class. If you take physics class, probably covered in physics 2, then you'll no doubt study waves in that class, and you probably have to worry about amplitude in that class, but you don't have to worry about amplitude in this class. So we're just primarily going to deal with the wavelength and the frequency and the speed. So if this is an electromagnetic wave traveling in a vacuum, say in space, then its speed is a constant. and its speed would be 2.998 times 10 to the 8 meters per second. So that would be the speed of light, right? Okay, so that's some basic features of a wave. So now let's look at what is the relationship between wavelength, frequency, and energy of a wave. And so you want to get accustomed to these symbols, right? Lambda is wavelength, nu is frequency. So, and we'll say the wave is propagating in this direction. So we have two waves propagating from left to right on the screen, and at the same speed. So which wave is of higher energy? And so if it's not obvious to you, then I like to use an analogy. Let's say that this is an ocean wave and you're at the beach, and you're at the beach where the waves are breaking. So you have some waves coming in. So which would be higher, longer wavelength and shorter wavelength? So this would be long wavelength, and this would be short wavelength. And which would be high and low frequency? So this would be low frequency, and this would be high frequency, right? So if those two waves were coming at you, which wave's going to wear you out the fastest? Which are you going to have to expend the most energy to oppose? And that would be the one on the bottom, right? So this is of higher energy, and these waves are of low energy. So basically, as you increase the wavelength, then that's going to decrease the energy of the wave. So energy and wavelength, right, are inversely proportional to each other. Whereas if you increase the frequency of the wave, right, so that would be this wave on the bottom, higher frequency. If you increase the frequency, then that's going to increase the energy of the wave. So energy is directly proportional to frequency of a wave. As frequency goes up, energy goes up. As wavelength goes up, energy goes down. So what's the relationship between wavelength and frequency? So you can see here that as the wavelength goes up, then the frequency goes down. Whereas if the wave gets shorter, if the wavelength, the distance between the waves gets shorter, so as wavelength goes down, since they're moving at the same speed, then as the wavelength goes down, if they're moving at the same speed, then more waves are going to pass per unit of time. So as wavelength goes down, frequency goes up, and then energy goes up. So as wavelength goes up, frequency goes down, and then energy goes down. So the relationship between wavelength and frequency is inversely proportional to each other, right? As one goes up, the other goes down. So wavelength is inversely proportional to frequency, right? As wavelength goes up, frequency goes down. As wavelength goes down, frequency goes up. So there's some couple of key equations in this chapter that relate frequency, wavelength, and energy. So one of them is c, which is the speed of light, is equal to wavelength times frequency. And the other is energy is equal to a constant called Planck's constant times frequency. And that is equal to 6.63 times 10 to the minus 34 joules times seconds. So we'll do some calculations with these equations throughout the course of these lectures, but that's two key equations in this chapter that you want to know how to use. So there's a little bit of math in this chapter, probably about the first third of the lecture, first half of the chapter is doing calculations. And these will be two of the equations, and the other half of the chapter is purely conceptual. It doesn't require any math at all. Okay, so the electromagnetic spectrum. So what are the different regions in the electromagnetic spectrum? So what are the different forms of electromagnetic radiation? So I'll give you one just to let you know what I'm talking about. So one will be like visible light. And the other forms of electromagnetic radiation, you could have radio waves. So see if you can list the other 5. So visible, radio, microwave, gamma rays, infrared radiation, UV, and what am I missing? X-rays. Right, so that would be the 7 different regions of the electromagnetic spectrum. So now let's put them in order, from high energy to low energy, left to right, or from right to left, low energy to high energy. So on the left we have long wavelength, and we have low frequency. And on the right we have high frequency and short wavelength. So which of these is the lowest in energy? And that's going to be the radio waves. So radio waves from to a frequency of about 10 to the 8th per second, or wavelength of about 10 meters. And then after radio waves is the microwaves region. So the frequency is about 10 to the 8 to 10 to the 12 waves per second, or about 10 meters to 10 to the minus 4 meter, right? So wavelength is getting smaller, frequency is getting larger. And then after that is the IR region, infrared, from about 10 to the 12 to 10 to the 14 per second, or down to about 10 to the minus 6, so about 1/millionth of a meter in wavelength. And then you have a very short, small sliver of a region called the visible region. So from about 750 nanometer wavelength to about 400 nanometer wavelength. So that would be the colors of a rainbow. So what are the colors of a rainbow in order? So it would be red, orange, yellow, green, blue, indigo, violet, right? Maybe you've heard this acronym before: ROY, first name, G, middle name, BIV, last name. So ROY, G, BIV is the colors of a rainbow in order, from long wavelength to short wavelength, or from low energy to high energy. Okay, so are any of these electromagnetic radiations dangerous? And the answer is yes. Oh, sorry, we didn't finish this. So what's after the visible region of the spectrum? Would be the ultraviolet. And then after all of ultraviolet, X-ray. And then after X-ray, right, would be gamma rays. So very high frequency, up to about 10 to the 24 per second, and very, very small wavelength, 10 to the minus 16 meters. Okay, so are any of these dangerous? And the answer is yes. So which of these are dangerous? Well, UV is dangerous, right? That would be why if you go in the sun for extended periods of time, you may wear sunblock to protect yourself from UV radiation, which can cause skin cancer. X-rays are dangerous, right? That would be, where might you be exposed to X-rays at? Well, you get some naturally coming in from sun, but you also could get exposed to X-rays right at the dental office, which would be why you wear a leaded vest. If you have dental X-rays done, or if you have other X-rays done, you would wear a leaded vest. So why do you wear leaded vest when you have X-rays done? Because lead PB absorbs X-rays, so that would protect your internal organs. And gamma rays are very dangerous. So you can get gamma rays exposure from radioactive material, and they can cause DNA mutations. So that can lead to cancer as well. So one of the reasons why our radioactive material is so dangerous. Okay, so just in terms of their speed, so radar wave, for example, can leave Earth, bounce off the moon, and return to Earth in 2.5 seconds. So traveling 478,000 miles in 2.5 seconds. So electromagnetic radiation moves extremely fast, right? Speed of light fast. Okay, so let's do some calculations. So A&M Commerce has a radio station. Not sure if you're aware of that or not. It's KETR. So where does it broadcast at? Well, it broadcasts on FM. So FM 88.9 on your radio dial. So what is that number, 88.9? So that number is a frequency of the electromagnetic radiation. So it's 88.9 megahertz. So what is the wavelength of this electromagnetic radiation? So let's calculate that wavelength. So we have frequency. So if you have frequency and you want to go to wavelength, then you need this equation, right, which relates frequency and wavelength. So this is given, and this is a constant. So you can solve for wavelength. So wavelength is simply going to be the speed of light divided by the frequency, right? So if we set that calculation up, so wavelength is equal to 2.998 times 10 to the 8 meters per second, and 88.9 on the bottom, and the units, that's 88.9 megahertz. So we can't just divide those out and that's our answer, right? We got to do a little bit more work than that. So what we need to do is convert megahertz to hertz. So we want megahertz on the bottom and hertz on top. So if you remember, what is the power for mega? It's 10 to the 6, right? So there's 10 to the 6 hertz and 1 megahertz. And then we need one more conversion, because what we have on top is we have units of meters over seconds, so 1 over seconds. So we need the bottom to be 1 over seconds as well. So to do that, we need to convert hertz, and this is an easy conversion. So 1 over seconds is the same thing as 1 hertz. So you're just multiplying and dividing by 1, but you're formally converting your unit that way. So now everything's going to cancel out, right? And you end up with the right unit. So megahertz is going to cancel, hertz is going to cancel. You have 1 over seconds on top and 1 over seconds on bottom, so that's going to cancel. And the only unit you're left with is meters, which is the distance, and you're trying to calculate a wavelength, so you need a distance to come out of this calculation. So the wavelength then is going to equal, so 3.37 meters. So to me, that doesn't mean a lot, because I don't think in terms of meters. If I think in distance, I think in terms of inches, feet, yards, miles, right? So let's, and most of you probably do as well, so let's convert this to feet, just so that you have a better concept of what this wavelength is. So 3.37 meters, and if we want to convert that to feet, then you need to know some conversion factors, right? So let's see. So one conversion factor that I just happen to know off the top of my head is that 1 inch is 2.54 centimeters. So I know I can get inches and centimeters, and then I can get meters to centimeters, and then once I get to centimeters, then I can get to inches, and once I get to inches, then I can get to feet, right? So let's see. So if we want to convert this to centimeters, so there's 100 centimeters, right, and 1 meter. So now my meters are going to cancel out. Now I'm in centimeters. And now I want the centimeters to go away. So there's 2.54 centimeters and 1 inch. So now centimeters will cancel out. And then we can convert inches to feet, right? So there's 12 inches and 1 foot. And so that would give you, so let's see, right? So meters cancel, centimeters cancel, inches cancel, and you're left with feet. So that would give you 11.1 feet, right? So that's an absolutely huge wavelength, but it's moving really, really fast. Okay, so what type of electromagnetic radiation is this? Well, it would be a radio wave. How do you know that? Because you're listening to it on your radio, right? Or the other way that you would know that is you would just look here and see which region it's in, right? So about 3 meters, so that's in the radio region of the spectrum. And so that radio wave, again, is moving really fast. It's moving at the speed of light, 2.998 times 10 to the 8 meters per second, which doesn't mean a lot to me. I know it's fast, but I don't think in terms of meters per second. I think in speed in terms of miles per hour. So if you converted that to miles per hour, you would see that that's 670,663,500 miles per hour. Okay, so if you have sunlight coming in, so light coming in from the sun, if you pass that through a prism or a crystal, what happens to it? So you maybe have seen this done before. Maybe you have a parent or a grandparent or you yourself have a crystal in the window. And what happens when light passes through that crystal is it'll display a rainbow on the wall, right? So you'll get red, orange, yellow, green, blue, indigo, violet displayed onto your wall. So question for you then. I can't even read it's hard to read my own writing here. So is a rainbow's, So is a rainbow continuous? Is there a constant or gradual change from one color to the other color where each of the color just blends into each other? And the answer is no, it's not. There's actually some regions in there where there is no color, where there's no light. So the colors do not blend smoothly from one color to another. So there are regions, or there's wavelengths or frequencies where there is no light. But this cannot be observed with the naked eye. If you have the right instrument, you can observe that though. So sunlight absorption spectrum, so basically it looks like this. So if we took this and projected this onto a wall, right, then that rainbow onto a wall, then what you would see from red to violet, you would see some regions in there where there's actually no light. So at 656 nanometers, right, there's no light. So there'd just be a black line there. And then at 486 nanometers, so this is red. So some red light is missing. There's no blue-green light. And then at 434 nanometer, so that's where blue light is at. So there's a strip where in this region of blue, there would be a portion where there's no blue light at. And this is at 410 nanometer. So at 410 nanometers, so this is the violet region, indigo to violet region, so there would be a strip of where there's no light there. So this would just be a nice or prettier picture of it. So, and what does this have to do with chemistry? Well, if you can understand why there's light and no light, then you understand something about the structure of the atom, is the significance of this. So this is all related to elements. So we can see hydrogen here. So at 656, there's no light. And it's because of the hydrogen in the atmosphere. Here at 486 nanometer, there's no light, and that's because of hydrogen that's present. Here at 434 nanometer, there's no light, so there's just a black line. And then at 410 nanometer, there's no light. And there'd be other regions in the rainbow where there's no light, and that would be due to the presence of other elements that sunlight would have came in contact with. And so that's our job, is to explain this, and then we understand something about the structure of the atom. Okay, so this is another experiment related to this. So if you took a tube of hydrogen gas, and then there's a wire in there so that you can pass electrical discharge through it around 5,000 volts. So if you do this, then hydrogen gas, so H2 gas will emit, it's blue, pink, it's bluish pink. It will emit bluish pink light, or blue pinkish light. Gee whiz, if I could spell. So now if we take that light and pass it through a prism again, then what happens is the prism will separate that light out into its components. And basically what you see is the opposite of this. You see regions where there's no light, but you see a red light line come out. and then no light, and then you see a blue-green light come out, and then no light, and then a blue line come out, no light, and then a violet line come out. So that's what's known as the hydrogen emission spectrum. So at 656 nanometers, you see red light. At 486 nanometers, you see blue-green light. At 434 nanometers, you see blue light. And at 410 nanometer, you see a violet light. So this is what's known as a line spectrum. So if you projected that onto a wall, then you just have lines where there's light at, and then in between there's no light. So when heated to a high enough temperature, hydrogen will emit red, blue, green, blue, and violet light. So this would be a little bit prettier picture of it. So you get 4 lines from hydrogen in the visible region of the spectrum. And again, so our job is to explain that. So basically all elements do this. All elements will emit light when heated to a specific temperature depending on what the element is. So sodium vapor, for example, will emit yellow light at 589 nanometer. So sodium gives off more intense light than most other elements and has practical applications since yellow light is not scattered as much as longer wavelength light. And the human eye exhibits a strong response to yellow light. So you see it utilized in fog lamps, as this picture here shows, street lamps. No, that's not fog lamps, that's street lamps. And fog lights on a car, for example, or warning signs. Although it's been phased out a little bit because, as you can see in this picture, sodium yellow light versus LED lights. LED lights give you a little bit even clearer picture at nighttime. So this is how you also explain fireworks. Where do the different colors in fireworks come from? Well, it depends on what element is in the firework. Strontium will give off red light, barium green light, copper blue light, sodium yellow light, calcium oranges light. So the different fireworks have different elements in them. So when those fireworks explode, a lot of heat is generated. And basically we're going to explain in the next lecture where these different colors come from, right? Neon, if you heat up neon to a high enough temperature, it gives off orange-red light. So all of these lights that you may have in your room, they have different elements in them, and we heat that element to a high enough temperature, it'll give off light. So why do elements give off light when heated? That's what we're going to explain in the next lecture. And that will lead to a more fundamental understanding of the structure of the atom. Okay, we'll stop there.